You're listening to DTFHN for April 17, 2026. I'm your load-bearing host, Jack Hacksman. We are your daily tech feed for Hacker News, a website where people rediscover good ideas and act like they invented them. Today's got that old bones energy, the kind where everything new turns out to be something ancient, wearing a fresh coat of paint. Let's dig in. One of the top comments on this thread cuts right to it. Someone points out the article itself is AI generated, the whole site. And honestly, that's kind of perfect. Because here's a piece about a language the industry ignored for 40 years, written by a machine that exists because the industry spent those 40 years rebuilding what Ada already had. There's a recursion there that's almost too neat. But let me play the other side for a moment. Maybe the industry was right to ignore seriously, a language designed by committee, mandated by the Department of Defense, wrapped in procurement documents named Straw Man, Wooden Man, Iron Man. This sounds like everything that kills innovation. Government contract language, top-down specification. The opposite of builder culture. The opposite of a hacker in a garage shipping something that works. Except. And this is where that argument falls apart completely. Look at what they actually built. Generics as a first-class feature. Concurrency in the spec, not bolted on as a library. Range-constrained types. Discriminated unions. A task communication model that Go would independently arrive at 3 decades later. Compile time, null exclusion. Language-level contracts. The separation of interface from implementation as a mandatory discipline. Not a suggestion. That's not committee bloat. That's craft, the kind of engineering where someone sat down and thought about what actually goes wrong in software and then made those things structurally impossible. Rust has been converging toward this from one direction. Python from another. C# has been approximating it feature by feature for 20 years. Every modern language described as innovative is on close inspection, rediscovering decisions Ada formalized in 1983. One commenter raises a genuinely interesting question. What's Ada's equivalent of affine types? What solves the onamite problem that Rust solves with its borrow checker? And that's the right thread to pull, because it points at the one area where the lineage actually diverges rather than converges. Ada chose a different path for memory safety, one rooted in access types and storage pools rather than ownership semantics. Whether that was a limitation of its era or a legitimate alternative design is still a live question. The real lesson here isn't that Alba was ahead of its time. It's that good engineering doesn't need a logo, a package manager with clever names, or a charismatic founder giving keynotes. Sometimes it just needs someone willing to say, the compiler should enforce this. The programmer should name what they mean. And ambiguity is a bug. 40 years later, every language in the room is nodding along. Ada just got there first and didn't bother telling anyone. Anthropic just dropped something worth paying attention to, and the benchmarks are only half the story. In 1997, the NSA proposed the Clipper chip, a piece of hardware that would give Americans access to strong encryption, but with a built-in backdoor so the government could listen in whenever it deemed necessary. The pitch was familiar. Powerful technology, responsibly managed, with safeguards that protect you from the bad actors. The Clipper chip died because the cryptography community pointed out the obvious. You cannot build a lock that only the good guys can open. The back door is the vulnerability. Anthropic just shipped Claude Opus 4.7. And buried in the announcement, between the benchmark charts and the glowing testimonials from fintech companies, is a fascinating admission. They have a more powerful model called Mythos Preview that they won't release broadly. Opus 4.7, they say, has had its cybersecurity capabilities deliberately reduced during training. They experimented with, and I'm quoting here, efforts to differentially reduce these capabilities. Follow that logic all the way to the end. A company trains a model to be extraordinarily good at understanding code, systems, and infrastructure, then surgically removes the part that understands how those systems break. But understanding how systems break is understanding how systems work. Security and capability aren't separable modules you can slot in and out. Every penetration tester knows this. Every developer who's ever written a fuzzer knows this. The knowledge of how a lock fails is the knowledge of how a lock functions. The comments tell the real story. Security professionals report that Opus 4.7 refuses to assist with authorized penetration testing, even after the model itself reads and acknowledges the program guidelines permitting the work. Anthropic's solution is a cyber verification program. Essentially, a permission slip to use the full tool you're already paying for. Meanwhile, the same users note that the model burns significantly more tokens to produce roughly equivalent results to its predecessor, with a bigger thinking budget. There is a version of this that's genuinely interesting. A company doing real research into capability control, publishing findings, advancing the field. And then there's the version where you ship a product with features removed and call it safety research. The Clipper chip also had a research program, the tools to understand systems. All systems, including their failure modes, should be available to the people building and defending those systems. A verification program is just a Clipper chip with better marketing. The lock that only authorized users can fully open is not a lock. It's a liability. So what happens when you stop gatekeeping the tools and just let people build? Story 3, Codex of almost everything. Let me work with what we have from the title and comments to write this segment. Based on the title Codex for almost everything and the HN comments, this is about OpenAI expanding Codex from a developer tool into a general-purpose agent for non-technical users. A professional agent product. The comments reveal comparisons to Claude Desktop, co-work, complaints about usage limits, pricing, and a tension between hiding code from coders versus empowering non-technical users. Here's the script. Let's talk about the fundamental constraint. Every software tool ever built sits on a stack of abstractions, and each layer exists because the layer below it was too hard for the next ring of users. Assembly to C to Python. Python to drag and drop builders. Each jump expanded the user base by an order of magnitude. OpenAI is now betting that natural language is the next abstraction layer, and Codex is the product. The pitch is straightforward. You describe what you want. Codex writes the code, runs it, gives you the result. Not just for programming tasks. For almost everything. Data analysis, file management, research, workflow automation. The kind of work that currently requires either technical skill or an expensive specialist. Run this forward 5 years. If this abstraction holds, if natural language reliably compiles to working software, you've just made every knowledge worker a programmer, not in the way that no-code tools promised, where you're still thinking in database schemas and conditional logic, in a way where the computer actually understands the intent and handles the implementation. That's a genuine phase change. Now here's what the comments reveal, and it's worth paying attention to. One commenter notes that Claude Desktop and Cowork already do most of this. Another points out that the UI seems designed to hide code from coders, treating the actual implementation as an annoying intermediate step. And someone who's used a CLI for 25 years admits they've started reaching for Codex instead of typing commands directly. That last one is the signal. When power users voluntarily move up an abstraction layer, the abstraction is working. But the architecture question matters here. This is a proprietary system running on proprietary models behind proprietary rate limits. One commenter upgraded to Plus and immediately hit another usage wall. The abstraction layer that turns natural language into software is extraordinarily powerful, which is exactly why it shouldn't be controlled by a single company's pricing page. The open source ecosystem is building these same capabilities. Agentic coding with local models, open frameworks, no rate limits, no bait-and-switch upgrades. The abstraction layer is real, and it's coming regardless. The question is whether it arrives as infrastructure everyone can build on, or as a service everyone rents. The engineer and achievement deserves appreciation. Turning fuzzy human intent into reliable executable code across arbitrary domains is genuinely hard. The teams building this, at OpenAI and everywhere else, are solving one of the most interesting problems in computer science. But the best version of this technology is the one where the abstraction layer itself is open, auditable, and forkable. Because an abstraction you can't see through isn't an abstraction, it's a dependency. We talked about tools you can see through. Pause, here's one you can see with. IfIM brings image viewing straight to the Linux framebuffer. Someone in the comments on this one mentions going weeks without a graphical desktop. Weeks. No window manager, no compositor, no desktop environment. Just a raw Linux console and a collection of tools like FIM that render images directly to the framebuffer. FIM stands for FBI improved itself, an improvement on an older framebuffer image viewer. And what it does is deceptively simple. It takes image files and draws them directly to your screen's memory buffer. No display server, no graphics stack, no intermediary standing between your pixels and your eyeball. There's a concept in architecture called the load-bearing wall. It's the wall you literally cannot remove without the building collapsing. Everything else, the drywall, the trim, the paint, is decoration. The framebuffer is the load-bearing wall of Linux graphics. It's been there since the beginning. X11 was built on top of it. Wayland was built on top of it. Every graphical environment you've ever used on Linux ultimately pushes pixels to this same primitive surface. FIM just talks to it directly, and the comments reveal something interesting about what this enables. People are building complete computing environments at this layer. MPlayer renders video to the framebuffer. FBPDF handles documents using Poplar and MPDF libraries directly. You can pipe marked file names from one FIM instance into another for batch processing. The key bindings are fully reconfigurable. There's a shadow directory system for browsing low-res thumbnails while keeping high-res originals accessible. This is not a toy. This is a complete image workflow running on the thinnest possible software layer. The reason this matters is longevity. Desktop environments come and go. Display protocols get replaced. But the framebuffer endures because it's the simplest possible contract between software and screen. FIM has survived the X11 era, and it'll survive the Wayland transition because it doesn't depend on either. Someone asked in the comments whether it works with Wayland. It doesn't need to. It operates beneath that entire abstraction. There's something genuinely important about software that chooses the lowest viable dependency. Every layer you add is a layer that can break, a layer that can change its terms, a layer between you and the thing you're actually trying to do. FIM is a program that displays images on a screen, and it does this by talking to the screen. Everything else is optional. 20 years from now, when we're on our third or fourth display protocol, tools like this will still work, because the wall is still load-bearing. Remember that bootstrapism idea? Here's maybe the purest example yet. But a Python interpreter that wrote itself in Python. What does it mean to understand a machine if you can rebuild it inside itself? This is a Python interpreter written in Python. Byte around 500 lines of code that can execute Python programs by re-implementing the same bytecode loop that CPython uses under the hood. And before you dismiss this as a parlor trick, a snake eating its own tail, consider what it actually demonstrates. The entire execution model of one of the world's most popular programming languages fits in fewer lines than most configuration files I've seen in production. Alison Kaptur and Ned Batchelder built this, and the article walks through it with the kind of clarity that makes you realize most computing education is overcomplicating things on purpose. The Python you write gets lexed, parsed, compiled to bytecode, and then a virtual machine executes that bytecode one instruction at a time. That's it. A stack, a set of frames, and a dispatch loop. One commenter said they went through an entire university degree hearing that programs run on stacks without ever actually understanding where or how. Then they read this and it clicked. That's not a failing of the student. That's a failing of every institution that buried a simple idea under layers of abstraction nobody asked for. There's a beautiful detail in the implementation. Instruction dispatch uses Gradder instead of a massive if-elif chain. You take the bytecode name, look up the matching method, and call it. Someone in the comments flags this as an elegant pattern, and they're right, but it's more than elegant. It's the kind of design that only emerges when you're building something to be understood, not to be impressive. Working code that teaches is worth more than clever code that performs. And this is open. The code is on GitHub. The article is free. The knowledge of how Python actually executes your programs is sitting there, available to anyone with a browser. Byteron is slow. Absurdly slow compared to CPython. And that's the point. Speed was never the objective. Comprehension was. You can read every line, modify every instruction, break it and fix it, and watch the stack do its thing. The tools exist. A language that lets you rebuild its own engine in 500 lines, and people who took the time to explain every one of them. That's builder culture at its best. We talked about building worlds in Minecraft earlier. Now let's build real ones. CadQuery brings parametric 3D cane modeling to Python. The default file format is step. That's a small detail on the CadQuery documentation page. Easy to scroll past, but it tells you almost everything you need to know about what this project actually is. STEP is an ISO standard. It's the format that real manufacturing shops accept, not STL, which throws away all the parametric information and hands you a bag of triangles. Not some proprietary format locked to one vendor's ecosystem. STEP. The format that says, this model carries its own engineering history with it. In 1999, Autodesk acquired a small company called Mechanical Desktop and began the long process of consolidating the CAD industry around AutoCAD and eventually Fusion 360. By 2024, they'd moved Fusion to subscription pricing, and engineers who'd built entire workflows around it woke up to discover their tools had a landlord. The models were still there. The freedom to use them on your own terms was not. CadQuery takes a different architectural position. Your model is a Python script. It lives in a Git repository. It has a commit history. It accepts parameters. You can run it on any machine with a Python interpreter, which at this point is nearly every machine on Earth. The geometry kernel underneath is OpenCAD, the same open source kernel that powers FreeCAD, maintained since the mid-90s. One of the commenters mentions building a rotary slide rule bracelet using Build 123D, CadQuery's sister library. A mechanical multiplication device designed in code, presumably printed on a desktop 3D printer. That's 3 separate manufacturing revolutions collapsed into one person's weekend project. The barrier between imagining a physical object and holding it is now a Python function and a spool of filament. Another commenter built an entire CAD platform, FluidCAD. Inspired by CadQuery's approach. That's the thing about open tools. They don't just solve problems, they become foundations. Someone else's library becomes your product's starting point. The knowledge compounds because nothing is locked away. A Python script that produces manufacturing-ready geometry, version-controlled, parameterized, running on an open kernel. The tools exist. The printer is warm. The rest is just writing the function. Now shift gears entirely. We've been talking about building things. Pause. Let's talk about why some tools stubbornly refuse to evolve. Let me make the strongest case for the status quo first. C, C++, and Fortran work. They have decades of optimized compilers, battle-tested libraries, millions of lines of production code, and an enormous talent pool. As one commenter points out, every new language in this space has to answer a brutal question. What urgent problem do you solve that MPI plus OpenMP plus CUDA doesn't? And if the answer requires rewriting a million lines of simulation code that already runs on 100,000 cores, maybe the rational choice is to keep what works. Hardware got 1 million times faster in 30 years. The languages didn't hold it back. Why fix what isn't broken? Here's where that argument collapses on its own terms. Core counts went from 80 to 11 million. Performance improved by a factor of 18 million. The hardware engineers delivered something extraordinary. And the programming models responded by bolting extensions onto languages designed before the internet existed. Pragmas, directives, annotations, layer after layer of complexity duct-taped onto C and Fortran, because nobody could afford the migration cost of starting fresh. It worked, but at what cost to the people writing the code? The question nobody in HPC wants to ask out loud is this. How much performance are we leaving on the table because the programming model makes it too hard for domain scientists to express what they actually mean? One commenter captures it perfectly. On their cluster, most of the real work happens in Python, R, and Perl. Not because those are fast, because researchers can think in them. MPI barely reached them. The gap between what the hardware can do and what a climate scientist or biophysicist can reasonably ask it to do is not a hardware gap. It's a language gap, an abstraction gap, a tooling gap. And this is genuinely beautiful engineering we're talking about. Dragonfly topologies, chiplet architectures, slingshot interconnects pushing data across 11 million cores. The craft in that hardware deserves admiration. The kind of admiration that makes you want the software stack to be worthy of it. Chapel, the language behind this retrospective, is open source. MIT licensed. Designed from scratch for parallel computing across shared and distributed memory. It compiles, it scales. And after 30 years of watching the HPC community choose the familiar over the expressive, Its creator is still showing up, still making the case, still putting the tools where anyone can reach them. The hardware engineers move the decimal point 6 places to the right. The question is whether we'll let the programming models catch up, or keep duct taping the ones we have until the complexity becomes its own bottleneck. Remember that 3-mi speedup we saw with agentic coding earlier? Turns out it worked for mobile too. Next up, BAWS, Android CLI. I've spent enough time wrangling Android build systems to know that the real bottleneck was never the code. It was the ceremony. The 40 minutes of SDK downloads before you write a single line. The emulator that won't boot because you installed Platform Tools version 33, but your project targets 34. The Gradle sync that fails silently because some environment variable points to a directory that existed on your old laptop. Google just shipped a CLI that collapses most of that ceremony into single commands. Android SDK install, Android create, Android run, and the numbers they're reporting. 70% reduction in token usage, 3 Vamanas X faster setup. Those aren't about making apps faster. They're about making the preamble disappear, the part where your agent burns through context window just figuring out where the SDK lives. Now, let's do the first principles thing. What does an AI agent actually need to build an Android app? It needs a compiler, a runtime, a way to push bits to a device, and documentation it can parse. That's it. Everything else is ceremony. An Android Studio is a lot of ceremony. A powerful, full-featured IDE that is also a 2 GB download with opinions about your project structure, your build system, and your workflow. The interesting architectural decision here is the skills repository, markdown files, that are basically machine-readable runbooks, not documentation for humans to learn from, but specifications for agents to execute against. That's a meaningful distinction, and they put it on GitHub, which means anyone can fork it, extend it, adapt it for their own tooling. Claude Code, Codex, whatever you're running. The skills are agent-agnostic by design. One commenter nails the real desire. This for iOS. Because Apple's toolchain is still welded to Xcode in ways that make headless development an exercise in archaeology. The strategic read is straightforward. Google wants Android development to happen everywhere, through every agent, because distribution wins. The more entry points into the ecosystem, the more apps get built. They're not locking you into their agent. They're paving the road and letting anyone drive on it. That's how platforms should compete. Make the on-ramp so smooth that leaving becomes a choice, not an escape. Moving on. One commenter describes letting Claude Code with Opus design boards and run SPICE simulations. It completely hallucinated the capabilities of the hardware, made claims so disconnected from reality that the commenter had to flag it as a warning. And honestly, that's the most important comment in the thread, because Lucas Gerads clearly hit the same wall and built his way through it. His insight is deceptively simple. Don't ask Claude to imagine what a circuit does. Give it eyes. Hook up an oscilloscope through an MCP server. Hand it a SPICE simulator and let it close the loop between simulation and physical measurement. The model stops guessing because it doesn't have to guess anymore. It can probe, measure, compare, and iterate. The same cycle any engineer runs at a bench, just faster. The technical discipline here deserves attention. Every lesson learned in this post is about constraining the model in exactly the right ways. Don't let it guess your physical setup. Don't let it construct flash commands on the fly. Give it a make-fail with explicit build, flash, ping, and erase targets. Don't dump raw oscilloscope data into context. Save it to a file and let the model interact indirectly. Each of these is a scar from a real failure, turned into a reusable pattern. That's engineering craft. What scales here is the workflow, not the demo. He's explicit about that. The circuit is trivial on purpose. The architecture underneath. Spice simulation feeding into physical measurement, feeding into automated verification. That's the skeleton for serious embedded development. Another commenter connects this to FPAA research. Field programmable analog arrays. Imagining a future where you could vibe code analog circuits the way we vibe code software today. We're not there yet, but the feedback loop is what gets us there. And the whole thing runs on open tools. Spice has been open source since Berkeley released it in the 70s. Claude Code talks to the oscilloscope through an MCP server anyone can inspect and modify. The makefile pattern is universal. Nothing here requires a vendor-locked toolchain or proprietary platform. An applied physics teacher in the comments immediately sees how this connects to education. That's the signal. When the tools are open and the workflow is documented, the knowledge compounds. Every engineer, every student, every tinkerer with a scope and a sim gets access to the same feedback loop that makes this powerful. So we've been talking about tools that accelerate engineering, but what happens when nature itself has an accelerator built into our DNA? Ingegneria Dieta, Human Genome Project launched with a promise. Map every gene, decode the blueprint. Understand what makes us human. But the most interesting discovery wasn't in the genes at all. It was in the spaces between them. IRE sits on chromosome 20. For 300 million years, across every mammal, bird and chicken that carried it, this stretch of DNA accumulated just 2 changes, 2 mutations in 300 million years. Then, in the 6 million years since humans and chimpanzees diverged, it changed 18 times. That's a 90-fold acceleration. Something was under intense selective pressure, and it wasn't coding for a protein. It was producing RNA, a regulatory molecule active in the developing human brain between the 7th and 18th weeks of gestation, precisely when the cerebral cortex is being architected. Let me play devil's advocate. Maybe this is noise. Maybe 18 substitutions in a short sequence is statistical coincidence, not selection. But the structure tells you otherwise. The human version of HAR1A folds into a completely different shape than the chimpanzee version. Different shape means different function, and it's expressed in Cajal-Retzius cells alongside reelin, one of the key proteins that orchestrates how neurons migrate into the layered structure of the cortex. The cortex that gives us language, abstract thought, the ability to build tools and share knowledge. The real weight of this, the thing that may have made human cognition possible, isn't a gene. It's a regulatory sequence. Not the blueprint for a component, but instructions about when and where to deploy components that already existed. The architecture didn't change. The orchestration did. This matters for how we think about intelligence itself. We keep looking for the magic ingredient, the single breakthrough. But HAR1 suggests that what separates human cognition from everything else that came before might be a matter of timing and organization. The parts were already there. Evolution just learned to conduct them differently. This has been your daily tech feed for Hacker News for April 17, 2026. This podcast is entirely AI-generated. Scripts by Claude Opus 4.6. Voice by Quinn3 TTS. Not affiliated with Hacker News or Y Combinator. Now go dig into something that's been waiting for you to notice it. We'll see you back here tomorrow.